Hello, my name is Bijay Krishna Saha, and this is a presentation of my course project for pattern cognition at University of Florida. The problem focuses on the face recognition problem and especially the implementation of the eigenface algorithm. So in this presentation, I'm going to go through the face recognition problem, highlighting some existing approaches. I will also talk in details on certain like the algorithm used here, which in this case is the eigenface method, its performance, and finally I will also draw a conclusion gathered from the algorithmic implementation and the test results that I've obtained. For a general problem given a photograph, the first action is to identify the faces in the image itself. So this can be done by looking for patterns of face in the image bitwise. Firstly, to look for common things like the eyes, the nose, the mouth, and etc. In the second step, we perform the face recognition to ID the subject. In some case, we can remove the first step whole if we happen to know that the image is clearly of the face itself. And in the end, we find a metric to match this accuracy of our finding. Here, the things to consider here are the accuracy and the speed. To increase accuracy, a threshold is needed to be chosen to remove or limit the false negative scenarios. Also, to find a compromise between speed and accuracy in selection of eigenvectors, pick as many eigenvectors that do not interfere with the speed so that it can be used as real-time system deployment. Here I'm going to give some applications where this face recognition system can be used. It is used in normal security systems. It is also used in law enforcement, in traffic cameras, in ATM cameras, and many others. It is used by the defense to perform subject identification and in some cases large-scale data processing. It is also used by social media sites like Facebook to tag people in images. So here I'm going to talk about the existing approaches. There are actually several existing approaches. Here I will go with the popular ones. First is feature-based. One example of which is the Weiler-Jones, which uses object detection framework. The second approach is statistical-based, which uses principal component analysis or the linear discriminant analysis. And the third is a hybrid of the above approaches, which is a mix of the first two approaches. So in this, I'm going to talk about the eigenface method, which is a statistical based approach. It uses the principal component analysis. So for an image which say 100 pixel by 100 pixel in dimensionality, so 100 pixel into 100 pixel gives 10,000 pixels. So computation happens to be very expensive. Sometimes scaling down is done to reduce this computational overhead. So for testing for experimental purposes, I have used the AT&T face database. It has got 40 subjects with 10 faces each having different expressions. The images are in 256-bit grayscales and of dimension 92 by 112 pixels. And the algorithm can be broadly divided into two phases: the training and the detection phase. In training, images are fed into the system and using the principal components and eigenspace is generated. In detection phase, weights of eigenfaces are combined to reconstruct the face, and the highest weight or the minimum distance is a resultant ID of the subject detected. Here I'm going to give an algorithmic overview of the training phase. In step 1, mean of all 10 expressions of the subject is calculated. Then transformation of the training images. In step 2, the training image is transformed into vectors. In step 3, we compute the mean of the face vectors. In step 4, we remove the mean calculated in step 3 to remove the redundant information. In step 5, we calculate the covariance matrix. In step 6, we compute the eigenvectors. If dimension of image is 100 by 100, that gives rise to a huge computational overhead. Instead, we use A transpose TA, taking advantage of lower number of subjects. In this case, it is 240. In step 7, your eigenvector selection algorithm is used. In step 8, the training images are projected into phase space given by the given equations. So here I'm going to give an algorithm overview of the detection phase. A mean phase is again removed to remove the redundancy. The resultant image is then projected into phase space, and in step 3 we identify a subject ID for a minimum Euclidean distance provided it is within a particular threshold, or a no match is returned. Alternate distance measurements could also be employed here, like the Mahalanobis distance. Chiefly, there are two sets of parameters which are needed to be chosen to increase performance. An eigenvector selection clustering technique is employed. The eigenvectors are clustered into two clusters. The eigenvector cluster corresponding to the eigenvector with max eigenvalue is chosen. In threshold selection, a proper threshold to minimize the occurrences of true positive and false positive events. Threshold corresponding to slope is equal to 1 on ROC. ROC curve gives the best selection of threshold. So here we come to performance evaluation, which is chiefly based on the accuracy and the receiver operating characteristics curve. We come to accuracy, which is measured on the number of accurate predictions over the total number of images in testing set. Here it can be seen that the recognition increases with the increasing number of principal components used. The receiver operating characteristics curve also corroborates the same finding, that the recognition increases with the increasing number of principal components. With a proper choice of threshold, it can be operated near slope is equal to 1. This will minimize the total number of true positive events as well as false positive events. Here we see that as we add more principal components, we get representations more close to the actual subject. You only need a maximum of 20 components to get 95% of good predictions. So finally we come to conclusion. So here in this presentation, we verified the application of PCA in the face cognition problem. It performs fairly well with the proper selection of parameters and in comparison to other techniques. Now I'll give a demo. So yeah, I'll first show the folders. So in this folder, the ATT faces, which contains the images of 40 subjects. So here I use the first 6 images for training and images. So here you can see that there are 10 images of 40 subjects. So here I use the first 6 images for training, and the images 7 to 10 are used for the testing, and results are computed and stored in the results directory, which can be found here. So now let me run some test cases. So what this does is it gives a plot of accuracy versus the number of principal components used with all the faces. Here we see that the recognition rate increases with increasing number of PCA components. We can also, and the results is saved in this particular file. We see that the most of the observations are correct, except for this instance, say it's a wrong result. So once in a while this happens. And then we come to, we can also do this, find this prediction rate with subjected to any particular PCA. For instance, here I using PCA is equal to 4. I'm sorry, I just need to close the results. And we see it gives a prediction rate of 58.125%. And I can also show you a reconstruction of the face with different PCA components, which is like, here I'm using subject 2. Yeah, so these are the faces. So we see that with increasing PCA components, the given image resembles more close to the actual image. So that's it. Thank you.